Hey everyone, this is Mr. Cure. This video is going to be looking at the Falling for Gravity lab you just completed. So what I'd like you to do is to ensure that you have your own Falling for Gravity lab that you completed in front of you. And as I'm going through this video, think of how your lab compares and please make any necessary changes. I want to make sure you have a really good lab you're handing in and give you some good feedback as a result. So what we're going to start off with is the introduction. So the introduction, all you're doing here is you're basically just giving some background information for the lab. So in this case, we're going to be explaining what acceleration is, how it's different from constant motion, and what causes objects to fall towards the ground. So first of all, to accelerate is to change the speed of something. So you're speeding up or slowing down. So remember, the objects were initially motionless, and what happened was when you released them, gravity pulled them down and they accelerated or sped up towards the ground. This is different from constant motion where objects are traveling at the same speed, and that's a significant difference here. Okay? Now, gravity is what's actually pulling the objects down towards the ground and causes them to accelerate. And things that could affect this could be the object's shape or size. In other words, the aerodynamics could play a significant role in this acceleration. So remember, the whole purpose behind this lab was to determine the effect of mass on an object's acceleration due to gravity. So first thing we did, we looked at a hypothesis. So what you do is you write down as the mass increases, this is what we're changing, you want to look what's going to happen with the acceleration. So you put down some kind of answer here. It doesn't have to be correct, but you have to be able to explain it. So in this case, the student wrote down that they thought the gravity will increase as the mass increases. And they gave a reason. And it's a pretty good reason because the gravity force has a greater pull on objects with more mass. So you can see it's a simple explanation, but still a good explanation. All right, now on to the observation table. So what we did is you should be looking at your observation table. And this is really key for most labs. You have a lot of marks for this table. You want to make sure that you organize it properly. So one of the first things you do is you include a title. It's going to explain what the table's all about. And usually it refers to the purpose of the lab. So in this case, we're looking at the acceleration of the falling objects. So we're going to have the acceleration at the end. And we're looking at the effect of mass. So a good title here would be the effect of mass on the acceleration of falling objects. You should tell me what the objects are doing as well. Now you want to make sure that the table flows. So you want to have any variables that you control on the right, and then any quantities that you're collecting, such as time, in the middle, and finally calculations and averages at the end. So let's take a look at our table here. So we have our drop height, which is not changing. We have our mass over here. You can see it's increasing as well. That's very important. Then we have our measurements, our average, and finally we do a calculation with the average. Things to keep in mind are this. Measurement units are only included in headings, never inside the table. So when I measured the time, I didn't write down 0.7 seconds, 0.7 seconds, etc. No, the units are only up here. So this would be the units in the heading itself at the top. So make sure you didn't put any units down in the actual table. Now, you want to make sure that the independent variable mass increases as you're going down. So you have an increase in mass. This allows you to better see trends in the data later on. It's very important. Anything that has a control should be in the first column. So that would be like the drop height over here. And the other thing is make sure you record measurements to the appropriate number of decimal places. Now, the number of decimal places is really dependent on your measuring device. So what I did is let's look at the decimal places. For the drop height, I thought that I was pretty well able to drop the objects within a centimeter or two of the actual height. So I included 2 decimal places. This means that I was accurate to a centimeter when I was dropping those objects. I recorded 2.00 meters. Now for the mass, all you do is you record the units that are in the display of the electronic balance, And the electronic balance we're using had 1 decimal place. You notice that all of these measurements have 1 decimal place, so a consistent number of decimal places. Time, well, this is where we had a bit of an issue. The time was the poorest measurement. We only had 1 decimal place because reaction time was such a huge factor here. So kind of keep that in mind. The other thing is that when we're doing any kind of calculations, they are at the end. And when you're doing the calculation, make sure you round to the correct number of significant digits. So when I did the calculation, this acceleration calculation, I used fall time and I used my height. And because my fall time only has 1 significant digit, my acceleration can only have 1 significant digit. So this is important at the end. Okay, so 1 significant digit in this particular lab for the acceleration, the calculation. Now let's look at the next quantity. The next thing you're looking at is a sample calculation. And now sample calculation is exactly this. You show me where your calculations are coming from, where your values are coming from. You only do this, for the very, very first object. So you don't want to do this, you don't want to show all the calculations necessarily. So what we do, we go into the observation table, pardon me here, and I'm going to do it for the ping pong ball in this case. So this object right here. So I'm going to use all of these givens here just for the ping pong ball and calculate the acceleration just for the ping pong ball. And I know that the other calculations are done exactly the same. You want to really show grasp method. It should be done very, very nicely. Include all units, formulas, therefore statements, etc. So I'm going to start with the given. So I know I've got my drop or fall distance of 2.00 meters. My drop time or fall time was 0.7 seconds, and my initial velocity was 0. I wasn't falling at the beginning. You indicate what you're looking for. So I'm looking for my acceleration here. Then you include the formula. So I'm using the d Witt hat squared equation here. And you simply substitute. I'd recommend doing this. So you substitute including units, you rearrange, and you include your answer with correct units. So here I'm going to have meters over second squared. Meters per second squared is my acceleration unit. And what you do at the end, you want to make sure that you round to, again, to the appropriate significant digit. So here I'm going to be rounding to 1 significant digit because I have 1 significant digit in the time. Now, next thing we're doing is the error analysis. Now for the error analysis, what you want to start with is you want to include the accuracy and the precision of the first object again. And we assume that the accuracy precision for the first object is going to be consistent with all the other objects. So we're going to figure out the accuracy of the acceleration, the calculation here for acceleration, and we're going to figure out the precision of these time measurements here. So that's the next thing we're doing. So let's go back to our calculation down here. So we're going to be using the MA equation for the accuracy. So it's percent error. So measured minus accepted over accepted times 100%. So here we have our measured quantity. Our first object's acceleration was 8 meters per second squared. The accepted value should be 9.81 meters per second squared. That should be the acceleration of any object. Doesn't matter what size it is or what mass it is, as long as there's no other forces such as air resistance acting on the objects. So that's our given quantity. So we substitute in here and we have a value of negative 18%. What this means is that the acceleration we calculated here was a little bit lower than what it should have been. Make sure in your final statement you round to appropriate significant digits. Here actually should be 20. And then include a statement saying, is the measurement above or below what it should be? So here, the measurements are 18% below the expected value. So make sure you include below, or if your measurement's a little bit too high, you put down above. Now, for the precision, what you want to do is you want to include the average and then show me the individual measurements. So here, remember, we're doing the time. We're looking at the consistency of the time measurements. And you can see here that all the measurements are very close. The furthest range here would be this 0.1 second. So we're only off by 0.1 seconds, the maximum. So we write down the precision as 0.7, the average, plus or minus 0.1. 0.7. 0.1 second. So we're only off by 0.1 seconds, the maximum. So we write down the precision as 0.7, the average, plus or minus 0.1 second. 0.7, the average, plus or minus 0.1 second. 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 0.1 seconds. So we could be above or below by 0.1 on average. Now, the next thing we have to do, we also have to explain any errors that were in the lab. So what we do is you list significant errors. What kind of errors that you really think might make a significant difference. Identify the errors instrumental procedural and tell me how this could have affected the data or results. Thirdly, describe a way you could improve the lab to reduce the impact of this error. So I have two different errors that we can look at. So the first one is one of the more obvious ones. It's the reaction time associated with starting and stopping the stopwatch. That's a big one. And what this does, it affects the time measurement and then subsequently the acceleration calculation. And finally, the drop time could be determined using a camera or motion sensor instead of using this stopwatch. Now, another average you could include would be maybe the shape or the size of the object. This could affect the aerodynamics, and if the aerodynamics are affected, it could reduce the pull of gravity, and this is going to change the fall time on the object. And what you can do to avoid this is to use aerodynamic objects, or at least try to make sure that the objects have the same size and shape. So the only factor really affecting them is the mass. And we saw in the lab, there are some really large objects, for example, the dodgeball, and some really small objects, a marble. And some of the objects are very, very light, such as a ping pong ball. So we could have a lot of air resistance with some of these. That could affect the results. Bottom line, you want to make sure you have these 3 steps in here. So again, identify the error, indicate the effect of the error, and finally, what you want to do is you want to indicate the how the error could be reduced. What can you do to fix it? Now, the final part is this, the conclusion. It involves 4 steps typically. Number 1, briefly summarize the results of your lab. You want to give actual values. You did all this work. You want to make sure if you did any calculations, you give them some due. So you want to talk about those measurements or calculations. Tell me the overall trend. What was the trend here? What happened, for example, to the acceleration as you changed the mass? Then you tell me how good the measurements were. So you comment on the accuracy, precision, and tell me how good the values are. Are the actual calculations valid or not? And basically, what you want to do at the end is you indicate errors as well. So indicate any kind of errors. So here's an example. So what I want to start with is, as shown in table 1, the acceleration was 8 meters per second squared, 6 meters per second squared, and 8 meters per second squared as the mass increased. So you're telling me what happened based on the table. Based on this data, there's no overall trend, and the mass does not appear to have a significant effect on the acceleration of gravity. So it does basically make sense that as my mass increases, really there is no change in the acceleration. Yeah, this middle value is off a little bit. That's probably because of measurement errors. Thirdly, tell me about the accuracy precision. So the data has an acceptable accuracy of 18% and good precision of 0.7 plus or minus 0.1 seconds. So the measurements were fantastic, very close. The accuracy was off, but not that bad though. Finally, you tell me, are the results valid? So, well, because the accuracy is okay, is fair, and the precision is good, it suggests that the results are valid. They're good results. And then you tell me about the errors. So possible errors in the experiment include reaction time associated with the stopwatch and the effect of air resistance on each object due to aerodynamics. So again, you want to use this as a little checklist for your lab now. One thing you want to keep in mind when you're doing labs, never ever use personal pronouns. Do not use I. Do not use we. Do not use our. Do not use my. Instead of that, what you can use is the. So the results, the data, the experiment. So please avoid personal pronouns. You're going to lose marks in communication if you do so. So that's it. So again, make sure that you look over your lab, make any changes. Don't make it exactly the same as mine, but you want to make sure that you incorporate some of the suggestions that I have, and then you want to submit it to me, and I'll give you some feedback with that. Okay, that's it. Take care.